Okay, so far the main benefits of considering this economy without network effect is that we have been able to introduce several tools that we are going to be seeing over and over again, such as how do you model consumer behavior, how does that lead to the demand curve, how do you think about a very simple model of production, so basically a perfectly competitive or a price-taking model, what is equilibrium in such a model, and how should you think of social optimality in such a model, right? So now we are going to take a step back and then consider the economy with network effects, which remember was our main objective. So we are going to motivate this through thinking about a model where you have got heterogeneous network effects, but you could have also thought about it in terms of a heterogeneous standalone effects. But this, I think, would make a bit more illumination on in terms of the main issues that are there. So imagine that as before, you have a continuum of consumers of mass one who are identified by a parameter theta, which is uniformly distributed on the interval 0, 1. So this is similar to what you had before, where remember we were labeling each number on the line between 0 and 1 with one consumer and one consumer with one number between the 0 and 1. So we continue to use the same thing. And imagine that for each consumer, the benefit that they get from having the good is given by this payoff function, which is this u theta, right? And that's equal to a plus theta v n e, right? So a is the standalone benefit. Theta is basically the identifier of the consumer. So different consumers have different values of theta. So higher the value of theta, higher the benefit that they get from having that good. V is basically a parameter which is taking into account the network effect, and NE is the expected number of people that they expect would be purchasing or using that good, right? So this is the gross benefit. In order to calculate the net benefit, you have to also take into account what is the price of the good. So imagine that the price of the good is P, then the net benefit from actually consuming this good is given by the gross benefit, which is this A plus theta V and E minus the price P, right? Now, what we want to do is derive the demand curve based on this model of consumer behavior. And in order to do that, the critical thing would be to find out the value theta hat, which would be the value or the identifier of the person who is going to be indifferent between buying or not buying this good, right? So how do we kind of find out that? So let's consider that the utility of payoff of not using the technology is normalized to 0, right? So then you are going to be indifferent if the net benefit of purchasing the good is going to be the same as the net benefit of not purchasing the good. So the net benefit of not purchasing the good is 0. What is the benefit of purchasing the good? So that is given by this expression that we saw in the previous page, which was A plus theta V and E minus P, right? So the person who is going to be indifferent, we are going to call that Miss theta hat, if you like, is going to be given by this theta hat, such that we have got A plus theta hat V and E minus P is going to be equal to 0. So we can use this to solve for a value of theta hat. So if you just reorganize this equation, so bring the P and A to the other side, so you end up getting P minus A and divide by V and E. So this gives you a value of theta hat, right? So if this is the person who is indifferent between buying and not buying the good, anybody who has a value of a theta which is more than this theta hat is going to be buying the good. Remember that the total mass is normalized to 1, so that the demand for a good at a price P is going to be given by 1 minus theta hat. Why? Remember, anybody who has a value of theta hat is going to be indifferent. If you have a value of theta hat, your net benefit from this purchasing this good, if you have a value less than theta hat, is going to be negative. And if you have a value of theta which is more than theta hat, your net benefit is going to be positive, which is more than the value of actually not having this good, which is normalized to 0, right? So then the demand is given by 1 minus theta hat, and this is what you get. Now, we have an expression here for n in terms of P and NE. We can rewrite this to have this as an expression for P in terms of other parameters, right? So what is this P? So this is telling us what's the willingness to pay for the nth unit of the technology when any units are expected to be sold, right? How do we get this expression for P? We basically use this expression and rewrote P in terms of the other variables, right? So you can multiply throughout by V and E. So then you end up getting on the left-hand side, V and E multiplied by N is equal to V and E minus P plus A, right? So if you now simplify, you end up getting this expression, and this is the meaning of this expression, right? So what is the willingness to pay for the nth unit? So this is the N that is there, right? For the technology when you expect that any amounts of these goods are expected to be sold. So we can also plot this, right? But before we do that, let's think about how to model expectations. So remember that we had these two different models of expectation, which are rational expectations and myopic expectations. So here, rational expectations would mean that in equilibrium, your belief about how many goods are going to be purchased is actually going to be matched in reality by the number of goods that is going to be purchased, so that your expected number of goods that is going to be purchased is just given by n, right? So if you set n equal to n here, you end up getting an expression which is Pn comma n, right? So we are setting n equal to n is equal to a plus bn multiplied by 1 minus n. So this is the demand curve, right, where we have put in the rational expectations, right? So we will call this the fulfilled expectations demand curve. Remember that another name of rational expectations is fulfilled expectations. So what is this curve doing in contrast to the curve that we had before, which was a function of NE? So this is telling us that for each price P, what's the adoption level N, such that when consumers expect exactly N adoption, then you are going to have n of them who is going to adopt price P, right? So let's break this down a bit. So we could have first drawn for different values of the expected value of NE, right? Different curves, right? So for example, this NE is just a parameter. So if you think of this as a constant, then you get that the price that is here, right? That's basically a linear function of n, right? If you think of this NE as a constant, right? So if you think of this NE as a constant, then for different values of NE, you are going to get these curves, which you can see are linear curves, right? So these lines that you see labeled as D1, D2, D3. So these are basically for different values of NE. So this D1, for example, is drawn for NE equal to N1. This D2 is drawn for NE equal to N2. So as you see that as the value of NE is increasing, this curve is kind of like going up, and these are all lines in the sense that the slope here is going to be a constant multiplied by 1 minus n. So therefore, it's an equation of a line, right? Now, in this curve, you could have actually found out for each of these lines, the straight lines that you have, what is the value for which, n1 is equal to, you put in the value here at for d1. Remember, this d1 was drawn with NE equal to n1. So you find out for at this curve, what is the value of this curve for n1, right? Similarly, for D2, find out the value of this curve for n2. And if you now draw and connect all these points, you end up getting this Pn comma n, right? So this is the expression that you get, where you are basically setting in n equal to Ne, right? And you end up getting this curve. Notice that this is clearly a quadratic function, right? You have got n multiplied by 1 minus n. You're scaling that up by v, and then you are adding a constant to it, right? So that is why you end up getting a curve, which is exactly this orange curve that you see, which is the standard quadratic curve, right? Okay. So if you now kind of like simplify this picture, right? So we now know that this orange curve is the one that we want to work with. That is the expectations fulfilled demand curve, right? And this black straight lines that you see, that is actually what is giving rise to this. So we kind of can work with the expectations fulfilled demand curve. Now we can think about for each value of P, what is going to be the demand. Remember that in the case when we were dealing with equilibrium without network effects, you had only one value of equilibrium, right? So for each price, there was a correspondingly a single level of demand. Here, on the other hand, that's not going to be the case. So it might turn out that in a model where you are dealing with network effects, there might exist more than one N that satisfies the equilibrium condition for a given price. So let's see how that works here. So suppose that the price was higher than the highest point of this expectations fulfilled demand curve. Now, what's the highest value of this expectations fulfilled demand curve? If we go and look at this expression here, remember that n can take value between 0 and 1. So A is a constant, B is a constant. So the highest possible value of n into 1 minus n is when n is equal to half, right? So then the highest possible value is A plus B by 4. So this peak that you see, that's A plus B by 4. So if you have a price which is higher than even the highest point, then in that case, the demand is going to be 0, right? But if you have a price which is in between A and A plus B by 4, then this price is going to cut this demand curve actually at 3 places, right? So the first two are obvious, but then there's also going to be the point where it's cutting at this intercept, and that's also going to be a demand. Now let's think about it why. So we are going to say that at this price, such that you have got price between A, so this is the A, and between A plus B by 4, which is this upper part, there are going to be 3 network sizes consistent with this price, right? Why is N0 equal to 0 price size, which is consistent with the price? So let's think about it. So imagine that if you go back here and you had expected that actually there's going to be zero people who are going to buy this good, right? Then what would your maximum willingness to pay for this good would have been? It would have been A, right? But we are seeing that the price of the good here is more than A, right? In this case, actually nobody is going to end up buying the good, right? So it is consistent in the sense that if nobody expects the good to be purchased, right, then nobody is going to be willing to pay more than the standalone benefit of the good, right? So in that way, n0 equal to 0 is a equilibrium. The other two equilibrium are coming in from the intersection of P with this expectations fulfilled demand curve, right? So set P equal to this. So you end up with a quadratic equation and you end up getting two solutions, right? So this solution, one solution is for a lower value of n. This is, let's call that n1p, and the higher is for n2p. And you can actually solve this, right? It's a simple quadratic equation and you end up getting these two expressions, right? So what does these two expressions correspond to? So the lower value, which is this n1p here, that corresponds to a case where consumers basically expect a small number of n to be adopted, right? That means that the consumers end up having a smaller valuation. Remember that your willingness to pay for the good depends on what you expect in terms of adoption, right? So if you expect a smaller number to adopt, right, then your willingness to pay for this good is also lower, right? So then you end up in a situation where you have a smaller valuation, and therefore the good is going to be end up being bought only by buyers with a large value of theta, right? Which is, remember, the heterogeneous network effects, right? You could have another equilibrium where you have got N2P, right, is going to be a solution. So this one is going to correspond to this case, right, where you are going to end up in a case where you have a situation where people expect a lot of people to adopt. That leads to a large valuation of the good, and then the goods end up being bought by a large number of buyers, but the last buyer is going to have a small heterogeneous network effect, right? So that is natural, because remember, we can actually rank the buyers in terms of their different heterogeneous network effects, right? So you basically end up in a situation contrasting to the one without any network effects, where you've got three actually sizes, which is consistent with a single price, right? So each of these equilibrium is relying on self-fulfilling prophecies, in the sense that if you expect nobody to buy, then nobody will buy. If you expect a small number of people to buy, then actually a small number of people will end up buying. And if you expect a lot of people to buy, then actually a lot of people will end up buying, right? So whatever is the expectation is getting fulfilled here, right? Now, in order to kind of like further the analysis, we have to figure out, how should we settle down on one particular equilibrium in this among these three cases, right? So the way we are going to do it is we are going to use stability analysis, right? So what does stability analysis mean? So think about how you thought about stability in the concept of equilibrium that you might have seen in other physics and engineering applications before, right? So we are going to call a particular equilibrium as stable if you allow for a small perturbation, then we are going to again come back to the original equilibrium, right? So that is basically going to be a situation which is stable, right? So let's compare these three different equilibria here in terms of stability. So the first equilibrium, which is nobody is buying, that is stable. Why is that stable? So imagine that you started out initially with this green point, right? Light green point, and you perturb things a little bit. So what does that mean? It means that, imagine that you suddenly have a small shock that leads to a small number of people end up buying this good. Now, is this sustainable? The answer is no. Why is that no? Because remember, this is the price they are paying for that good, right? But this blue line is basically showing what is actually their amount that they're willing to pay for the good, right? So these are people who are going to end up paying a higher price than what their willingness to pay for the good is, and they will kind of like not want to buy the good, right? So basically, any perturbation that leads to a small increase in n is going to generate forces that is going to again bring back n to 0, right? So in that way, it is stable, right? Because if a small perturbation is going to generate forces that is going to lead back to the initial equilibrium. What about the equilibrium corresponding to N1P? So here, two types of perturbations can happen. Either you start out with N1P and have a perturbation so that you end up with a smaller value of N, less than N1P, or a small shock so that you end up with an N greater than N1P. Now, we'll see that in this case, both of the situations, you're going to actually end up being driven away from this N1P, right? So let's first consider the case where a small shock leads to some people not buying the good compared to the situation where you had the number of people buying the good as N1P. So in this situation, basically now the price again becomes higher than the willingness to pay for the good, right? So then even more people are going to kind of stop buying the goods. So you end up with a situation where you are going to be driven away more and more from the equilibrium. What happens in the case where you had a small perturbation so that the number of people who are buying the good becomes higher than N1P? In this case, remember this blue curve is the willingness to pay. This green thing that you're seeing, this green straight line at P is the amount that you have to actually pay. Since the willingness to pay is higher than the amount that you have to pay, then you end up with a situation that more and more people would want to buy the good, right? So again, you end up away from this initial equilibrium of N1P. So this would suggest that this N1P is a unstable equilibrium. So because a small perturbation leads to further movement away from the initial equilibrium. What about N2P? Well, this is actually a stable equilibrium. How do you see that? Well, again, you can have two types of perturbations, either a perturbation which is bringing n below N2P or a perturbation which is bringing n above N2P. So if you have a situation where n is less than N2P, then that is going to be a situation where you have got the willingness to pay is more than the price of the good. So more people will buy. So you again move back to N2P. What about if you have a perturbation which moves n above N2P? So here again, the willingness to pay, which is given by this blue curve, becomes less than the actual price that they have to pay. So less people end up going to buy this good. And so again, n will fall till N2P, right? So again, you have got forces in the model that will push you back towards the stable equilibrium, right? So you've got this basically three situations, right? Two of them are stable equilibrium, and the third one is unstable equilibrium. Now, among these two stable equilibrium, you can imagine that the first situation is not really that interesting because the stable equilibrium is saying that in this market, nobody should buy the good. So if you were to kind of like consider how to kind of choose among these three equilibrium, first, you can use the criteria of stability to remove the N1P case. And then among the two remaining stable equilibria, you can think, okay, the interesting case is to analyze when you have a positive number of buyers buying. So you basically end up settling on this equilibria, right? So this is one of the criteria you can use, but this is a very standard criteria that is used to pick among different equilibria situations when you have got multiple equilibria. Okay, so that is the demand side. So that basically tells us that for each value of P, we can find out what is the demand, right? You can have multiple equilibrium then, but we have now figured out a criteria to use to rank this multiple equilibria case. Okay, so this is the demand side. What about the supply side? Now, again, as before, we are going to assume that the world is very simple and that there is a constant cost per unit cost of production. And this is going to be denoted by the parameter C. And we are going to assume that C is less than A plus V by 4, right? Why are we going to assume that? Basically, if you have got C is strictly less than A plus V by 4, and you have got the perfect competition assumption, we know from before that price is equal to the cost, right? So this is what we had even in the economy without network effects. So then basically we are dealing with a world where the price is basically going to be such that, we are going to be in a world where it's A plus B plus 4, right? So if you end up with a situation where C is so low, so that you are even below this A, right? So then the price is going to be below this A. So then in that case, the number of units that is going to be sold is 1. But if you're going to have a situation where price is more than A, but is still less than A plus B by 4, then the amount of goods that is going to be sold is N2P, right? So that is how you can find out the equilibrium in this market. So as a function of C and A, if C is less than equal to A, then the total amount of goods that will be sold is 1. But if C is more than A, then the total amount of goods is going to be given by this expression that we found for N2P, right? And that's exactly this expression that you see here, right? Now, notice one thing that if you have got basically this C is more than A, and remember P is equal to C in this perfect competition setup. So then this expression that you see here, NC at the end, right? This is going to be an expression which is less than 1. How do we see that? Well, this P minus A by V is something positive, right? So 1 by 4 minus something positive in this case is going to be something which is less than 1 by 4, square root of 1 by 4, and therefore it's going to be less than half, and therefore you are going to end up a situation where this last expression that you see, that's going to be something which is less than half plus half or less than 1, right? So in a perfect computation setup, if the cost is high enough, then the total amount that is going to be supplied eventually in equilibrium in the market is less than 1. Now, why is this important? Because we can also do a similar analysis to think about from a societal perspective, from if we were maximizing the societal benefit, what would have been the optimal amount of goods to be supplied, right? So here we rely on the analysis that we did before. Remember that from the consumer side, the way to think about what are the benefits to each consumer is to think about the difference between the benefit or the reservation price minus the price actually the consumer has to pay, right? So this is the expression that you see here. That is, remember, the net benefit to each consumer. And this is for the person who is of type theta, right? But who are the people who are buying this good? If n goods are supplied, these are the people whose value of theta is between 1 minus n and 1. And this is a continuum, so we can do integration from 1 minus n minus 1, right? This is the benefit that is going to each consumer. And what about the benefit that is going to each seller? Remember, the seller is selling n goods, right? And for each of the goods, the seller is getting this price, right? But this is the cost of production. So the seller is basically making a profit, which is equal to this expression that you see here, right? So now if you think about it, this expression P and N is not dependent on theta. So you can kind of like integrate this easily. So this will be minus n times P and N, which just cancels with this n times P and N you see here, right? So this expression simplifies to this integral that you see here, right? Intuitively, the reason why this PNN does not matter is this is basically a transfer from the buyer to the seller, right? So anything that if the buyer pays more, it's the seller is getting more money. So in net, there is going to be no welfare effect, right? So therefore, the welfare is given by this expression that we see here. Now, U theta n, we can actually plug in this expression that we already had right at the beginning, right, from here, and we end up getting this expression that you see here, right? And you can also kind of like get this expression for NC, and this is the expression that you eventually end up getting, right, for welfare, right? So by plugging in all the expressions that we have, right? And if you now actually do this maximization, you can show that this is actually going to be maximized. Remember that the highest value of n that we can select is 1. And in fact, you can show using calculus that the highest value for this expression is going to be for when n is equal to exactly 1, right? So what that means is that social welfare is maximized when all the consumers join network, right? But here is the significance. This is where the social welfare would have been maximized. But remember, we also showed that if you have the market forces operating, you can end up with an allocation where you end up with an equilibrium quantity being produced, which is less than 1, right? So this is a result which is different from what we found before. In the world where you did not have any network externalities, we had seen that the market on its own is going to produce a competitive outcome, right? Where you are going to have the efficient amount of output being produced, right? So remember the analysis that we did for the economies without network effect. Here we are showing that in the presence of network externalities, you might actually end up with a quantity which is less than the efficient amount, right? The efficient amount, as we saw in this calculation, is at n equal to 1. Here we'll end up with a situation where if the cost is high enough, where you end up with a situation where actually the amount of output being produced in equilibrium is less than 1, right? So you have got basically an example of what is known as market failure, right? So it's market failure in the sense that the equilibrium outcome reached by the market does not maximize the social welfare. And the reason why this happens is basically because you have got an externality sort of effect, right? What is the externality effect? The externality is that consumers, when they're deciding whether they want to purchase the good or not, they don't take into account that their purchasing the good actually provides more benefit to people who had already kind of purchased the good, right? So there's this side benefits that are accruing to people as a result of you deciding to, for example, join this network. And hence, because they are not considering, they are not taking this into account, they are just basing the decision on the basis of their own benefits. Therefore, you end up with a situation where you have got basically too little adaptation of the good, right? And if you have got large enough production costs, firms on their own cannot internalize this externality effects. And as a result of that, in the world with network goods, you end up with a situation where you have got under provision of these goods, right? So in some sense, you have got too little of this network goods being produced, right? So that's a very interesting application, because you might have kind of like heard this in economics, that there is a result which says that the market on its own often produces the most efficient outcome. So here we see an example where that is indeed not the case, where in the presence of this network externalities, you have a situation where the market on its own is not going to produce the most efficient outcome.